Really, this is now my vacation from the vacation, so it's really nice to be here. And I'd like to talk about interactive verification of distributed protocols using decidable logic. So I have to have this first slide saying why we need to verify distributed systems, although I think we all know why we need to verify them, right? They are everywhere now. They are in critical systems. They are in applications that we use daily. So it's very important to have them work properly, correctly, but unfortunately it is very difficult to get them to work properly. They can be very tricky, and even when we are looking at very simple protocols, they can have subtle bugs, and testing is not as effective as we would like it to be for these protocols, so we would really like to verify them formally. But formal verification of distributed protocols or systems is unfortunately also very hard, because if we look at a protocol, we usually want to verify it for when it runs on any possible system, which means that we have to deal with an unbounded number of threads or processes or nodes. We have usually an unbounded number of messages and so on, and all of this makes the state space infinite. So we are dealing with verification of infinite state systems, and then we know that generally it is undecidable to formally verify such systems, and also in practice it is very difficult to verify them. Okay, so that's what I had to say. And if we look at the approaches that are used in formal verification, we can roughly divide them to automatic approaches, like abstract interpretation and model checking. And when we use these approaches and we apply them for infinite state systems, then we know that because of undecidability, they are ultimately limited, which means that, for example, sometimes we may use abstraction, but then we may get false alarms. Or it may be that these approaches, these techniques that we use will not terminate. Or sometimes these approaches restrict the kind of systems that they can handle. So in any case, automatic techniques are limited, so they cannot really handle all systems that we may want to verify. And then, on the other hand, there are deductive techniques, either using some automated solvers or using interactive theorem provers. And deductive techniques are very expressive, and they can verify very complicated systems, but the downside there is that usually they require great user effort. The user has to provide some annotation. If we look at approaches that are based on automated solvers, then the user has to provide annotations, but also these automated solvers are sometimes diverging, and their behavior is sometimes unpredictable, which means that they may work sometimes, but even when you make small changes to your system, they may stop working, and it's very difficult to understand why and what's happening, and the user has to understand the heuristics that are used in order to make the solver works, and so on. And if we look at interactive theorem provers, so they are very predictable, the user is in control, they are writing the proof, but then the proofs are usually very long, and again, it requires a lot of effort from the user. So to summarize, if we look at these approaches in comparison, we have these deductive approaches based on proof assistance or automated solvers, and they are very expressive in the kind of systems and proofs that they can verify, but they are ultimately limited because they require a lot of effort from the user. And on the other hand, we have these automatic approaches that are great because they are completely automatic, but they are limited, and they have to be limited because we know that the problem is undecidable, so they cannot handle all systems. And what this talk is about is trying to find some new trade-offs in this space by interactive verification. Okay, so in interactive verification, we have the user, the human user, and we have the machine, solver, or whatever automatic procedure that we want to use. And the idea is we want to somehow divide the verification task between the user and the machine. And what we would like to have is still maintain a high degree of automation. We don't want the burden on the user to be too high, so like to be on the end of the scale there. But we also don't want to sacrifice expressiveness too much. And we want to to have a predictable approach. We don't want to have what is sometimes happening with SMT solvers, that they diverge and you don't really understand what's going on. It's important to have the approach comprehensible for user or intuitive for the user so that the user can somehow understand what's going on, and we would like to have an efficient approach overall and so on. So we have a lot of goals that we would like to achieve, and the main questions are basically how will we divide the work between the user and the machine. So what would be the role of the user, what would be the role of the machine, and how will they interact? And in this talk, I want to present three attempts to realize this idea of interactive verification, so three forms of interactive verification. The first is basically just deductive verification, where we use decidable logic, and this lets us have an iterative process where the user interacts with the system based on counterexamples to induction. The second is going to be more fine-grained, use a more fine-grained interaction where in each iteration we help the user adapt the invariant that they create. And the third approach is closer to automatic invariant inference, and here we want to let the user guide the inference. And maybe this didn't say much, but I will now go over it. Okay, so this is basically what I want to do. I talk about these three approaches. And all of these were realized in Ivy, which is a verification system developed by Ken Macmillan. So you can ask Ken all about Ivy. I will not talk about Ivy so much. Okay, and I'd like to start with some background. So in Ivy, you can now verify very complex properties, temporal properties, but in this talk, I'm only going to talk about safety verification. And in safety verification, I assume we all know, we have, so suppose this is some state space of a system, maybe an infinite state system, and we are given a safety property that describes, that specifies some bad behaviors that should never occur in the system. For example, if we are looking at a lock server, which is what I'm going to use soon, then the safety property can say that there cannot be a lock that is held by two clients. So the bad states would be that a lock is held by two clients or more. And the system is safe if all the reachable states satisfy this property, so none of them is bad. And when we want to verify safety, especially when we talk about infinite state system, one of the prominent ways of doing that is by finding an inductive invariant. An inductive invariant is a property, some formula that describes a set of states and satisfies these three requirements. So it has to include the initial state. It has to satisfy consecution, which means that it is preserved by the transitions of the system. Okay, so which means that if we make a transition of the system, starting from a state that satisfies the invariant, then we have to go back to a state that satisfies the invariant, and this is not allowed. Okay, we cannot have a transition from a state that satisfies the invariant to a state that violates it. And it also has to satisfy safety, which means that it has to be, sorry, this was premature, which means that it has to be disjoint from the bad states. So if we find such an inductive invariant, such a set, then because of initiation and consecution, because it includes all the initial states, and because it is closed under the transition of the system, we know that it includes all the reachable states, and therefore, because of the safety requirement, we can conclude that the reachable states are disjoint from the bad states, and we verify safety. Okay, so basically to do safety verification, we need to find such an inductive invariant. Okay. And these requirements here define some verification conditions. If I give you the inductive invariant, then now you can translate these requirements to verification conditions that correspond to validity checks of these implications in logic, or equivalently, you can think of them as checking unsatisfiability of these formulas. Okay, so these are the verification conditions. Okay, so when we think of this, of safety verification using inductive invariants, then we can see three challenges that we have to deal with. The first is the challenge of specification. How do we even describe the system, and how do we describe the inductive invariants and the properties? in a way that is expressive enough and that we can actually do the verification. The second is the challenge of deduction, of checking the verification condition, discharging the verification condition. And this is often undecidable. Even if we use first-order logic, then checking validity is undecidable. And the third challenge is the challenge of inference. How do we actually find the inductive invariance? And the key idea in IV is to restrict the verification conditions to decidable logic in order to at least take care of this issue here, and the issue that checking the verification conditions is itself difficult. And IV supports several decidable logics, but specifically in this talk, I'm only going to talk about EPR, which is very simple. EPR is a fragment of first-order logic. It is uninterpreted first-order logic, so there are no theories, which means, for example, we have no arithmetic. But on the other hand, we can use quantification in a restricted way. We can have exist for all quantifiers in this order. And quantification is very useful, especially when we want to talk about distributed protocols and when we want to say something about all the nodes and we don't have a bound on the number of nodes. So quantifiers are very helpful in this. For example, talking again about the safety property that we had before, that a lock is held by at most one client. So we can specify it using quantifiers for every x and y. If x holds the lock and y holds the lock, then they are equal. Okay, so it's very nice to have quantifiers. And the reason why we choose EPR is that this is a decidable fragment of first-order logic, which means that checking satisfiability is decidable, and also checking unsatisfiability is decidable. So it means that discharging the verification conditions is decidable. And decidability is a theoretical concept. So you can say, well, decidability just says that it will terminate eventually, but this eventually can be too long. But our experience shows that when working with decidable fragments of logic, and specifically when working with EPR, this decidability is not just theoretical. It also has some effect in practice. And really working with it has a very predictable behavior, and it usually terminates quite fast. So it's not just theoretical, it's also practically useful. Another nice property of this fragment of EPR is that it has the small model property. And this means that when a formula is satisfiable, it not only has a model that satisfies it, it has a finite model that satisfies it. And this will be useful because for us, when we check the verification conditions and they don't hold, then this means that the formulas are satisfiable. And this property will mean that we will get a finite counterexample to induction. We will have a finite example explaining to us why the invariant is not inductive. Okay, so these were the nice things about EPR. It gives us this decidability and finite model property. And now, on the other hand, we restrict the language that we can use to describe the verification conditions. So this may have a price. So a nice thing is that the price is not actually in modeling systems. EPR as a modeling language is Turing complete, which means that we can describe any system that we want using EPR. But the restriction comes when we talk about the properties that we want to verify and the inductive invariance that we want to specify. So here we do have a real restriction, which means that it can prevent us from verifying some systems that we may want to verify. But now there is already a list of works that use EPR for verification in different domains, for example, for shape analysis and software-defined networks, and more related to this talk, distributed protocols. So even though EPR is limited in some way and does impose some restrictions, it's expressive enough to verify a whole bunch of systems. And I believe that Ken and Oded will talk about it more this afternoon. So back to the challenges. Now, when I want to use EPR for the verification, so this challenge of deduction is now, for me, dealt with, okay? Because now it is decidable, and like I said, it's not only theoretically decidable, we see that in practice it really makes checking the verification condition predictable and fast and efficient. The formal specification part, well, like I said, it now is more limited and can become more challenging, but I put a V here because I will not talk about it here, and I hope that you believe me and wait until Ken and Oded's talk to hear more details. But what I want to focus about in this talk is really how do we find the inductive invariants. And specifically, I want to talk about how we can find or infer these inductive invariants interactively. Okay, and I want to start from an example that I will use throughout the talk. So this is a simple example taken from the Verdi project. And this is a protocol, a distributed protocol that implements a lock server. So we have a server that has some unbounded number of locks, and we have an unbounded number of clients that may want to acquire the lock. The protocol works in this way. When a client wants to acquire the lock, it sends a lock message, a lock request to the server. Then, when the server receives a lock request, it may send a grant message to the client. And you see now the lock is no longer available here, but it is not yet taken by the client. Then when the client gets this grant message, it holds the lock. It invokes a receive lock action, and it holds the lock. Then it may hold it for a while. When it wants to release the lock, it will send an unlock message using this send unlock action. When the server receives the unlock message, the lock becomes free again, available again, and that's basically the protocol. Okay, very simple. And the safety property that we would like to verify here is, like I said before, is that a lock is never held by more than one client. Okay, very simple. Okay, good. So the first thing that I want to show is how do we model this protocol using Ivy or using EPR. Okay, so the first thing is that in order to describe the state of the protocol, we are going to use, the state is basically going to be a first order structure. So we are going to set some vocabulary and use this vocabulary to describe the state. So in this example, we have locks and we have clients. We don't explicitly model the server. So we will have two sorts, one for a lock and one for a client. And then to describe the state of the server, we will use a unary relation free that remembers which locks are available, free. We will have, to describe the state of the clients, we will have a binary relation held by, which says that this lock is held by this client. And to model the state of the network, we will have relations that track for us the messages that are in flight in the network. So we have three kinds of messages in this protocol. We have lock messages, grant messages, and unlock messages. For each of them, we have a binary relation, remembering that this client, that a lock message is pending for a lock message was sent by this client, and it requests this lock, and so on. Okay, so this is the vocabulary that we are going to use, and now a state of the protocol is just a first order structure that defines some set of locks, some sets of clients, and defines some interpretation for all these relations, telling us which lock is free, which lock is held by which client, and so on. To describe the transitions of the system, the actions that are executed, we are going to use Ivy's modeling language, which lets us define actions. And the way we describe actions, it's very similar to an imperative language, except that we can update relations using first-order formulas. So for example, this action here, the send lock action, this is when a client requests a lock, so it sends a lock message to the server. So this will just be done by updating the lock message relation for this client and lock to be true. And this true here is just a first order formula. It could be a more complicated formula if we wish, and so on. So this is one action, and here we will have in total 5 actions. And you should think of each action as atomic, but they are executed in any order. And these actions are translated automatically by Ivy to a formula, an EPR formula, that is going to be the transition relation formula. This is a formula over two vocabulary where the primed copy of the vocabulary is used to describe the next state. So for example, this section here is translated to this part of the transition relation, saying that there exists a client and a lock, such that you see that the lock message prime after the change is basically going to be the same as it was before, except that we are going to add the tuple where the first element is the client, and this C client, and the second is this L. So we update it by adding this tuple to the relation. And we have to say that everything else remains the same. Okay, so eventually we use IV's language, but eventually what we can think of is that we have a transition relation formula in EPR, in logic. And we'll also specify the set of initial state and the safety properties using formulas, using EPR formulas. For example, here we can say in the initial state description, we can say that for every client and lock, initially there is no lock message from the client to the lock. Okay, and so on. We will have to say it for all the relations. To specify the safety property, we'll specify the bad states. So the bad states here are just saying that there exists a lock and two clients C1 and C2, such that the lock is held by C1, it is also held by C2, and C1 and C2 are different. Okay, so there is a lock that is held by at least two clients, two different clients. This is the way we model the system. And now, when we want to verify the system, we also have to provide an inductive invariant, and we will have to provide an inductive invariant such that the verification conditions will be in EPR. And if we manage to do that, then now IV can take all of this and create for us the verification conditions. And since they are in EPR, then we can use an EPR solver. This is a decision procedure. Specifically, IV uses Z3, but you can use any solver that you wish. And the solver is guaranteed to terminate, at least theoretically, but also practically for us. And either give us a proof, which means that we verify the system, or gives us a counterexample to induction. And now I just want to emphasize that because we model the system in this way, using quantifiers, and we never specify in any way what is the number of nodes or clients that we are looking at, or what is the number of locks, then when we verify the system in this way, or when we verify the protocol in this way, then we verify it for any possible realization of it. No matter on what system it's actually going to run on, it's verified, okay? Because we verify it for any number of clients and locks. Okay, so the question now that I still didn't address is how do we provide the inductive invariant? How do we find it? And like I said, what I want to do in this talk is talk about how we do it interactively. Okay, so now we get to the point, interactive invariant inference. And I want to mention these three forms that were on one of the slides earlier. And I'll start with the first. So this is the basic form of interaction that you have in Ivy, where the interaction is based on counterexample to induction, and the user, you, when you try to verify the system, would have to provide you would have to model the protocol in Ivy's language. You will have to, of course, specify the property that you want to verify, and you will also have to provide the inductive invariant. Then Ivy will check the inductiveness for you. It will generate the verification condition and so on, and either give you a proof or give you a counterexample to induction. Just to remind you, a counterexample to induction is a pair of states where the first one satisfies the inductive invariant, the candidate inductive invariant. It's not an inductive invariant if you find it, but the first one satisfies your candidate inductive invariant, but the second does not, and they are connected by a transition of the system. And when this happens, when you get a counterexample to induction, you know that you failed to verify the system. It doesn't mean that the system is incorrect. It may just mean that the inductive invariant is not good enough. But it can also mean that the system is incorrect. So this is where this counterexample goes back to the user, and it is now the job of the user to understand whether they need to change the description of the system, whether they have to change the description of the property. Each of them could be wrong, or the most frequent thing is that they would just need to update the inductive invariant. Either strengthen it, maybe it is not maybe it is not strong enough, or weaken it. So this is the basic form of interaction, and the nice thing is that because we use EPR, the counterexample to induction is finite, so it can really be displayed to the user can look at it and can try to understand what needs to be fixed here in order to manage to verify. Okay, so if we go back to the log server example that I just had, the user can be optimistic and just try to start by providing as an inductive invariant the safety property itself. Maybe it is already inductive and then everything will be fine. So here, both the property and the first attempt for an invariant would be that for every lock and two clients, if the lock is held by both clients, then these clients are the same. And now, if we try to check if we use IV with that and we try to check inductiveness, then I believe that you can guess that it's not yet inductive. And this is really what IV would tell us. And it will also give us this counterexample to induction. And the counterexample to induction, again, it's a pair of states where one satisfies the candidate invariant, the second does not, and they are connected by a transition of the system, an action. Here, what we got is that we see that if we start from a state where we have this client holding the lock, but also there is a grant message for this client, then in one step of performing the receive lock action, this client will also hold the lock. Okay, so this is what we get here. You see, this is already a violation of our candidate inductive invariant, so this is a counterexample to induction. And of course, you can see that this state, where we have that the lock is held by this client, but also there is a grant message, is not really possible. It's not a reachable state of the system, but the current candidate inductive invariant said nothing about it, didn't exclude it, and this is why we got the counterexample to induction. So now we, as a user, we look at this, we say, oh, of course, but we should also say that this is not possible. So we will update the inductive invariant. We'll add another conjecture saying that this is not possible. It cannot be that we have a grant message from C1 to L, but also that C2 holds L. And now we can try again and say, is this now an inductive invariant? We can ask IV. IV will again give us counterexample to induction because it's still not inductive. And we can go on until we get this inductive invariant. And when we look at all these conjectures together, the conjunction of them, this is an inductive invariant, and we manage to verify. Okay, and we can do this again using a decision procedure and EPR solver. Okay. So this. Well, it's not exactly, because I don't know how I could do it not by hand. It's not that, okay, maybe I will get to it a bit later, but it's not that I exclude exactly this state. I, as a human, when I see this counterexample to induction, I see this state that I want to exclude. If I just excluded this state precisely, I wouldn't have terminated. So I do some generalization also as I do it. So I do it by, yeah. But this is what. No, you are completely right. Definitely. So if you are a user that doesn't really understand the protocol, you could end up doing that, just excluding this state, then getting another counterexample that just increases the number of clients or the number of locks, and then you wouldn't terminate as a person. But the idea is that this is meant for someone that knows the protocol and understands why it is correct. It's just that, you know, and looking at some formula and understanding whether this is already inductive is difficult for a human. You have to think of all the cases, all the possible transitions that would fire. So here you try something. If it's not there yet, you get some indication as to what you need to fix, and now you, as a human who understands, has to figure out how to change it in a clever way in order to avoid this non-terminating process. Yes, so this is, again, it's still in the context of deductive verification. The user has to do it, but the advantage is that the user knows that for every candidate inductive invariant that they provide, because of the EPR-ness, they will get an answer, and if the answer is no, they will also get some finite counterexample that is usually reasonable to look at and to get some intuition. That's the advantage here. Okay, and this form of interaction was used in a series of works that some of them I listed before, and we used it. So I'm not going to talk about these columns in the table. Just want to give you a feel of the kind of protocols that we managed to verify. Oded mostly managed to verify, and Ken. So we had some small protocols, but we also verified some variants of Paxos, which is a consensus protocol, and so on. We also verified some liveness properties that I didn't mention, and so on. This is the main form of interaction that you use when you use Ivy. But still, we would like to assist the user a bit more. We don't want the user to have to write down all these conjectures one by one. And the question is, how can we do that? And this is what we try to do in another work that was presented in PLDI 16. And so what we try to do here was help the user in each iteration of generating an inductive invariant, of generating a new conjecture for the inductive invariant. And this work targets specifically universally quantified inductive invariants. If you think at the inductive invariant that I just showed you of the log server, all the conjectures there were universally quantified. And this is a quite simple form of inductive invariant. This is what we focus on here. If we look at such formulas, universally quantified formulas, or inductive invariants in our case, we can think of them as just trying to exclude some bad behaviors. For example, if we look at these conjectures, this is just the safety property itself. What it is actually saying is that there cannot be a lock and two clients such that the lock is held by both of these clients. It just says this state is not possible. Then if we look at the second conjecture that we just added, what it says is that this state here is not possible, that the lock is held by a client, but there is also a grant message to a different client. And we can continue in this way and look at all the universally quantified conjectures, and each of them is just saying that some state or some partial state is not possible. So basically, a universally quantified invariant is, you can think of it as just a set of excluded states, and we can exploit this and also try to infer in universally quantified inductive invariant exactly in the same way, by finding such bad states, bad behaviors, and exclude them using universally quantified formulas. And there is a very natural way to do that, to look at a state and exclude it by a universally quantified formula. And the way to do it is by using a model theoretical notion of a diagram. So what is a diagram? Given a finite state, for example, this state here where we have one lock element and two client elements, and these are the interpretations of the relation, the diagram is an existentially quantified formula that introduces an existential quantifier for each element in the domain. So we will have the x here is an existentially quantified variable that represents this element, and y and z represent these elements. And then the rest of the formula will describe exactly the interpretation of all the relations and constants, if we have them, on these elements. Okay, so for example, you see that this lock element here, the red one, does not satisfy not free, so we say here not free x. We have the held by relation here, so we have the held by atom here in the formula. Okay, so we introduce existentially quantified variable for every element, and then we encode the interpretation of all the relations and constants on these variables. And the property that we get when we do this, when we write this formula, is that this is a formula that is satisfied by the model that we started from, and it is also satisfied by every model that includes it as a substructure. Okay, so for example, if we look at this sigma prime here, you can see that if I project it on these three elements, the red, green, and orange one, then it becomes exactly identical to sigma. So sigma prime includes sigma as a substructure. And really, it also satisfies the diagram. And if I look at this state here, again, it includes sigma as a substructure, and it satisfies the diagram. Okay, the diagram is satisfied exactly but by all the states that include sigma as a substructure. So in this state, talking about abstract interpretation, you can think of it as the best abstraction of this state when I restrict you to use only existentially quantified formulas. Okay, so if I can only use existentially quantified formulas, this is the smallest formula, smallest set of states that I can represent that include sigma. And now if I want to exclude sigma, and I'm limited to using only universally quantified formulas, then I will just negate the diagram. And this will exclude sigma and also exclude every state that includes it as a substructure. And again, this is the best that I can do, the most precise that I can do if I can only use universally quantified formulas. Okay, so this is great, but sometimes what I would like to do is actually not be so precise. Sometimes I don't want to just exclude sigma and everything that includes it as a substructure. This is the smart part. This is where the user gets into the picture. Sometimes I know that there are some things there that are not really relevant, and I don't want to say anything about them. So I can make this state partial. I can say, for example, I don't care whether this lock here is free or not. This is not important for me. I want to generalize it away. And then I can construct the diagram for this partial structure. So again, it will exclude this and every state that includes it as a substructure. But now, because it says nothing about this free relation, it will also, for example, exclude this state where here the lock is free before it was not free, and so on. So it gives me some additional generalization. And just to get more intuition, again, if I look at a universally quantified invariant, like I said before, I can think of it as a set of excluded substructures. Why? Because I can always write this formula in CNF form, which means it will be a conjunction of universally quantified clauses. Okay? And then each universally quantified clause is actually the negation of some existentially quantified cube, which excludes some partial state and everything that includes it as a substructure. Okay, so basically, this is the form of the negation of the invariant, and the invariant is just the complement, all the rest. And what I want to do is basically find these partial states here and construct their diagrams, and this will give me the inductive invariant that I'm looking for when I know that I'm looking for a universally quantified inductive invariant. And in this PLDI 16 work, what we wanted to do is find these partial states interactively, together with the user. And how? So the idea is, again, we are inside this loop, these iterations, where the user gives the description of the protocol and the property and the candidate inductive invariant. And let's think of this invariant as a conjunction of universally quantified conjectures. And then when the user gets a counterexample to induction, now the user wants to add another conjecture in order to exclude the CTI that they got. So what we will do is Ivy will display the counterexample to induction. It is finite, it can be displayed. And it will display one that is minimal. I don't want to get into that, but the user can specify some metrics based on which to minimize the counterexample to induction. And again, we can minimize because of the EPR property. So it's something that is reasonable for the user to look at. Now the user, this is the smart part, this is where the user uses their intuition. The user will have to generalize the counterexample to induction and mark which facts in this state, in this counterexample to induction, are actually not relevant, are not important, and can be generalized away. And this will be just using a graphical interface. The user has checkboxes and can say, don't consider the free relation, for example. Okay? Now Ivy can automatically translate the partial state that remains here using the diagram to a universally quantified clause that excludes this state and everything that includes it as a substructure. And Ivy also provides some additional checks that can help the user. For example, the user can now use bounded model checking to make sure that they didn't exclude an unreachable state, and so on. And then the user eventually decides whether they want to keep this conjecture that was constructed together by the user and Ivy, and this will give us the next conjecture, and so on. Okay? So this is the second form of interaction, where in each iteration, instead of letting the user just write down the conjecture, now we do it, we come up with a new conjecture together with the user, using a graphical interface. Okay. And we use this form of interaction also to verify some of the protocols that I had in the previous list. All of them have universally quantified invariants, so we could do it. But still, even now, the user is still involved in generating every conjecture. And the question is whether we can do better. We don't want the user to have to do it one by one. So in another work about automatic invariant inference, we had an extension of PDR that allows it to infer universally quantified invariants. And there again, the key idea, even if you don't know PDR and don't know the details, it's not very important. The main thing was that we used basically the diagram as an abstraction of states. And this is the way we could lift PDR that works with propositional formulas to work with a universally quantified formula. And make it and let it infer universally quantified inductive invariants. But again, this is a fully automatic approach. We used UPDR when in this paper we evaluated on heap manipulating programs, and it worked quite well. And we actually see that it also works well for some distributed protocols, but we know that ultimately it is limited. Okay, again, the problem is undecidable. We cannot expect it to handle everything. And what we wanted to do now is take UPDR, which is fully automatic, but find some way to let a user guide it to finding the right inductive invariant, not let it cope completely automatically with generalization, but somehow help it. And the question is, again, how? So this is what we tried to do in a recent work. And the idea in this work is we tried to add structure to the inductive invariants, make them structured in some way that is intuitive to the user, and then the interaction is by letting the user provide only the structure and letting a tool, UPDR, fill in the rest of the invariant. So let me explain to you what I mean by adding structure to the inductive invariant. So this is how the inductive invariant that we had before for the example. You see it had these 9 conjectures, and when you look at it, it's just a set of conjectures that say some things about the reachable states, and it's really difficult to see any structure here, just a set of facts. But instead, another way to be convinced of the correctness of the protocol is to look at it differently. Remember that we want to verify that every lock is held by at most 2 clients. Okay, so let me convince you. So if I look at some lock, it's for every lock, but let's think of an arbitrary lock, then we know that initially in the protocol the lock is free. Then, when a grant action is performed, the permission to this lock is granted to the lock L. Then, when this action, the receive lock action is performed, the lock is taken. Then we have send unlock that releases where the lock is released, and receive unlock that brings us back here. So the protocol from the perspective of the lock goes through these phases, and the changes in the phases are by these actions on the edges. We also know that there are more actions that could happen in the protocol, but these actions would not change the phase from the perspective of this lock. And there are also actions that we know that cannot happen in certain phases. For example, here where the lock is still free and there is nothing yet, we know that there cannot be a receive lock action. Okay? So this is a way to describe the proof from using phases. And when I describe these phases, it's now very easy to see that the protocol is correct, because now here, in this phase, I know that no one holds the lock. The lock is free. So of course, there cannot be 2 clients that hold the lock. Here, I know that permission is granted, but still no one holds the lock. So of course that the property holds. In this phase here, because here no one had the lock, and now just one client got the lock, then at most one client holds the lock, which is what I wanted. And here again, no one holds the lock, so the property holds. It's very easy to see that in every phase, the property that I wanted to verify holds. Okay, so this is the intuitive explanation for why the protocol is correct. And to translate it into a formal proof, we need to replace these words that I wrote there in each phase into formulas that characterize each phase here. And we need to do it in a way that it will become inductive. So this is now an adaptation of the notion of an inductive invariant to an inductive phase invariant. And the key differences, so we still have initiation and safety. Every phase, the formula of every phase has to imply the safety property, and the formula of the initial state formula has to imply the formula of the initial phase. But the interesting thing is the consecution. So when we talk about inductive invariants, we know that they have to be preserved by any transition of the system. And now we basically split these requirements based on the edges of this automaton, of this phase automaton. So we require, for example, here that if we start from this formula, the phase characterization of this phase, and we make a transition using this action, we have to end up in a state that satisfies this. Okay, so instead of talking about every transition, we now need to look at the transitions on the edges of the automata. And there is another requirement, and that is that we didn't miss any transition. Remember that some of the actions here, I said that they are not passable. So there is another requirement saying that really the phase characterization is strong enough such that all the transitions that can really happen are covered. Okay? If I start from this characterization of Q0 and I take a step of TR, then this step has to correspond to one of the transitions that is really there in the automaton. I didn't miss anything. If all of these properties are satisfied, then we can show that this automaton simulates the system, and therefore it really proves the safety. And this, I see that I'm running out of time, so I'll just say a few more words. Basically now we can use this as a basis for interaction. We'll just let the user give us the structure. Let's skip to this. Just what are the phases without characterization and the transitions that go between them. And we will automatically infer the characterizations. And we can do that by a variant of UPDR. Just can extend UPDR to finding these phase characterizations. And this is what we really did. Okay, so I will skip this. Okay, a nice thing, I will not say much about it, but a nice thing is that one of the outcomes is really that we find phase characterization, universally quantified ones, and then we are happy, we verified. But another outcome is that we found an abstract that we found a counterexample. We didn't manage to find phase characterization, but instead we found some abstract trace. I don't have time to get into the details, but the nice thing is that if we find this thing, this abstract counterexample, even though we don't know whether there is a safety violation, we know that there are no universally quantified phase characterizations, which is nice. So let me skip now the proof for why this happens and go just back to this slide. So eventually this is like the third form of interaction that I wanted to mention. Here what we do is we let the user specify the protocol and the property and the phase sketch. The sketch can be just the structure of the automaton, but it can also include some partial characterizations of the phases. And then we use phase UPDR to infer the phase characterization. If it succeeds, we are happy. If it doesn't, then again, we get some abstract trace, and now we can use this trace in order to understand how we need to fix what we provided to the tool. Maybe we need to change the protocol, maybe the property, and sometimes we need to change the structure. Sometimes we didn't attempt to structure the proof correctly, or in a way that is good enough, such that there will be universally quantified characterizations. And so on. So this is, again, a basis for an iterative process. I'll skip this. And to evaluate it, we looked at several protocols, and we looked what happens when we just use UPDR without any guidance, and when we use, in contrast, a phase structure, we just provide the automaton, and here we used also some we provided also some partial characterizations of the phases, and we can see that even with the phase structure alone, usually we get a very nice speed up of at least 2, and in some cases more. With the phase sketches, sometimes we get more improvement, but also sometimes it actually deteriorates, so it means that it's not always better to provide some additional data. The nicest example is this here. This is the most complicated example that we tried, and this is a sharded key value store, where when we just tried to use UPDR without any guidance, it didn't terminate in 3 hours. And then when we just provided the phase structure, it reduced to 40 minutes. So you see it's still a lot, okay, 40 minutes, but better than non-termination. And when we also provided some very, very partial phase characterization that only specified the essence of every phase and not the rest of the details, this reduced now to 3 minutes. Okay, so I think I will skip and just summarize. So this talk was about interactive verification using decidable logic. So I didn't always emphasize it, but the fact that we use decidable logic was important in every step, including for UPDR or phase UPDR. This was again important because this is what ensures that UPDR makes progress. Every check that it does is decidable because of this EPRness. So it was very important for us. And we saw, I mentioned 3 forms of interaction. One that is just deductive verification, but when you can use counterexample to induction to guide the construction of the invariant. We looked at a more fine-grained interaction where in each iteration, the user using a graphical interface can come up with the new conjectures. And the last form of interaction was more to the end of automatic invariant inference, and there we saw how we can take an automatic invariant inference tool and provide some guidance by providing a structure of the invariant or the proof. And the point is really that we know that we would like to have as our procedure as automatic as we can in order to relieve the burden from the user, but we cannot count on fully automatic techniques. So we need to find a way to interact with these automatic tools and understand how to divide the problem between the human and the machine. And it's very interesting to look at other logic, other inference schemes. How do we do it for abstract interpretation? And it's, of course, one of the most challenging questions is here. What can we say about all of this theoretically? What are the limits? What can we actually say here? And that's it. Thank you.
Thank you, Sharon. Questions? Ken.
So clearly there are limits to the scalability of the interactive invariant generation techniques or the automated ones like UPR. And so I guess the gist of my question is there a point where as we have increasing complexity of the system that we want to move away from the interactive and the automated techniques because they're less effective? Or is it more effective to try to think about how to always decompose the problem into small enough pieces that you can do all the inductive invariants by these kind of interactive techniques?
So what is the alternative? Are you asking whether we should abandon this and go back to just manual proofs?
Well, as opposed to not using the interaction, not getting automated help to do generalization of the counterexamples, but just doing the generalization in a completely manual way, which is the other possibility.
Yeah, so it's all a matter of, I guess, how useful you would like it to be, because some people will do the work completely manually, and some people use Cork as if it's the easiest thing in the world. But still, I think it's limited to a certain class of people that are willing to do that. And for others, I guess automation is important. It may be the only thing that will get them to do this. So I don't know whether you can always decompose the system into small enough pieces such that it will be possible to do it. But then you could combine it with other things. You can combine it with abstraction and verify not the implementation like we do, but just protocol.
So you think it's more a question of the user than the question of scale that would make the difference?
Well, I think both of these approaches have their space, but the more automatic you can get it, I think it is better, as long as you can maintain the other important properties that when it doesn't work, you can understand what happened, and yeah.
Okay, we'll start.
I have a small question and a big question. The small one is, I think it's more or less like a predicate abstraction where you have a basic choice of predicates, and the problem is if one is missing, you will never get the invariant.
What do you mean by the basic predicates?
You
Here?
see all the lock, this basic thing that you define. You might have an invariant which is not expressible by the primitive of the program, and you need a new notion.
No, so that's a bit different.
Like one process is before another or thing like that. If you miss it, you cannot express it.
No, but these predicates, the atoms that I have in the diagram, they encode all the relations. So it's not, I don't fix,
No,
I
but
think.
your predicates are a name plus parameters.
No, but I can then generate
You can
the
introduce new
universally.
names.
Yes, because of the
Automatically?
quantifiers. So I can introduce the quantifiers, and these are, what do you mean by name? So I have, for now, for this presentation, I had no functions. So I couldn't so there are no names that I could generate. The only names of parameters are just constants or variables. And I can generate more variables because I can generate quantifiers, so they go together. I don't know if this answers your question. So in predicate abstraction, the way I understand it, you would say, I have this predicate for all x, lock x, for example. And I can use it, but I can never use for every x and y, locks x and not lock y, or something like that.
Yes, the lock that is in my question is this word lock, if you don't have it and you need it in the proof.
But
you don't
so
have an example like this?
I don't have an example like this because this lock comes from the description of the system. So you would have an example where you don't, when you describe the protocol itself, you don't talk about a lock, but you need it for the proof. Everything that exists in the description of the system, I can then use when I construct the inductive invariant. So if I don't have this lock, it means I didn't have it in the description of the system. I had no lock.
Okay. And I have my difficult question. I see you have a tried chord, the protocol chord, which is an interesting protocol because it has been wrong for 20 years. But you say it's simplified.
So I have to point this question.
So how much work do you need? Because I think without arithmetic you cannot do it. They have to count something.
So the verification of the chord protocol was not of the full protocol.
I know because it's very complicated.
But I can refer you to Ken because
Right. So I used Pamela Zave's model. So she has corrections to those things, right? So it's not from the original, it's the model that Zave used. And she verified it for a fixed number, like 7 processes using alloy. And so we did it just for an arbitrary number of processes.
Okay.
But it's the same model that she used.
Okay. Good.
Let me ask you something. You started with APR that has A star, then all the invariants you generated are A invariants. So obviously in the transition relation you take these.
Yeah.
So what do you assume is the structure of the transition relation, and have you tried generalizing for more general invariants that are not only A invariants?
Okay, so the transition relation is EA. Well, I must say that this is all a simplified description, because when you use many sorted logic, as we do, like we have the lock and the client, you can go beyond exist for all as long as you don't have cycles when you look at the sorts. Why is that? I don't see the question. I don't see the relation to EPR.
Then you may need more than an EA. Right.
So in the invariants, we can use anything as long as eventually the verification conditions are EA, and which, okay, so it could be any Boolean combination of universally quantified formulas, but it cannot be EA in the invariant, because when you construct the verification conditions, you have the invariant both positively and negatively. So you have EA, it becomes also AE, which you cannot. But again, when you have sorts,
in some cases you can do it, right?
it will not be decidable unless you have the sorts that
You
can.
can have small model theorem anyway.
Yeah. You are correct, but it's not within the fragment. It's not within EPR, so we don't do it now.
Any other questions? Let's thank the speaker again and coffee break.
Thank you.